Hello, my dear J Warriors. I know you guys have been waiting for long. Welcome, Salu Janvi Harborain. Good evening, Nikhil. Good evening, Joseph. Hello, good evening, my dear lovely lions. Today evening, we are going to complete circular motion, the concepts, right? All the things for your J examination with your physics master teacher, none other than your Capto, your Captain Shreyas Sir. Exactly. And if you do not know about me, you can meanwhile read this slide. And I find extreme pleasure in teaching, and obviously I love physics and producing ranks. And one of the best way to do that is by providing the best content in English medium, which nobody else is doing for the last several years, for all the students who want to learn from the best of the best teachers on the Vedantu J English channel, guys. And make sure you are subscribed, and make sure you quickly smash that like button and mark your attendance in the road series. All the warrior pandus are here. Good evening, Alekia. Hello, Nikhil. What does WPW mean? It means warrior pandus. Whistle podu. Exactly. Hi, Shriyari. Hi, Bharadwaj. Hi, NN1. Good evening. So, till last lecture, we had completed work power energy. In case you are not aware of where to find these lectures, as you are on this channel, you can go down, you can see complete physics, complete maths, complete chemistry. There is this entire playlist over here, right from the first chapter of 11th as well as the 12th standard being conducted simultaneously. After circular motion, I'll be moving on to magnetism. I know many of you are waiting for it. So guys, watch the Newton's laws, vectors, 1D, 2D, electrostatics, current, etc. All these lectures are right over here. Even ray optics is done. So that is where you will find it. And also, very, very important thing, before I forget, let me show you that there is this entire sheet which is called as the Jungle Book. When you log in, you will get all the lectures, notes, the DPPs, everything at one single place. It will take time, but it gets updated every week. Okay, so that is your one place for finding all the content of this channel. Okay, be it PYQs, everything. And also, do not forget the test series for your scholarship is about to begin, where you can claim up to 100% scholarship and win lots of prizes, which is called as the MVSAT, Mega Vedantu Scholarship Admission Test. It's not just for admission, but it is also for knowing where you stand. You will also get free some of the study materials and scholarships for all the courses and all the things that you like to buy, be it the notebooks, be it the textbooks, be it problem solving books, be it the crash courses, be it some pedagogy app. So scholarships on that as well as national level ranking. So the link is there in the description box. Enter your mobile number and register soon, because remember, online the test is in mid-October, offline also it's starting 29th September. Okay, so that link is there over here. So let's begin, guys. Yep. Good evening, Sudhakar. Yeah. Ashwin, most of it will be done by October, most of the portions, right? All the important high weightage will be done by October. Okay. Yeah. So, starting off with circular motion, there is a very unique way of studying this chapter, and let me tell you, not many people will tell you this, and that is the reason why you will find this lecture very, very interesting. When I say circular motion, you start thinking about merry-go-round, giant wheel, the motion of the hands of a clock or your watch, or somebody going round and round in circle, a wheel spinning, the planetary motion, right? All these are examples, fan rotating, motor rotating, right? All these are examples of circular motion. Even pendulum swinging back and forth is a circular motion. But I'll make it even more general, and I will make you see circular motion in a very different perspective. Say for example, my dear warriors, okay, there is a particle, and this particle starts from here, and just imagine it is going along this particular path. This is the path taken by the particle. Now let's compare this with a normal circular motion. A normal circular path would look something like this, maybe. A normal circular path would look something like this. This would be a proper circular path with some radius. of course, and some center with some radius as well as some center. This would be the radius, this would be the center of the circle. Now, this path looks like a normal 2D motion, but let's think a little bit. When this particle is going in a circular path, at any given instant, it describes an arc of a circle, then describes another arc of a circle, then another arc of a circle, another arc, and so on and so forth. So there are many such arcs which are covered during the motion, of that particle. Small arc. Every arc has the same curvature. Curvature means how curved it is. That is calculated by how much the radius is. Every arc has the same radius. That means same curviness. And you continue, you will land back at the same place. Is that right, my dear warriors? But then, over here, this is some random path. I feel this random path can be also broken down into small arcs. But the main difference is these arcs which are basically like small paths have different curvature. They have different curvatures. All these arcs, they basically have different curviness. Here, it's probably a big part of it's a part of a big circle. Here the curviness is more. Here it is less. Here it is even less. Here it curves more. And they bend also on different sides. How about, thinking of extending that arc and making it look like a circle? How about extending that arc and making it look like a circle and making it feel as if it is a part of a circle? And there will be many such circles right over here. Maybe one over here. Maybe this over here, like this. Maybe like this over here. Maybe like this over here. This is slightly big. Maybe over here. Can you see, as the particle goes, it goes from one circle to another circle of different curviness or different curvature. Their centers are different, their radius are different. So can I think as if any two-dimensional motion, any 2D or basically 3D motion is nothing but a combination of many arcs of different circles, So actually, even projectile motion is a circular motion, but different circles. Any motion, an ant moving somewhere is a circular motion, but different circles. A mosquito flying in the air is also following many circular paths, but each of the circles are different at different instants. Isn't it? Ashwin will try to complete as much as possible. It all depends on how your attendance, everything is. But major portion by October. That's what I would say, Ashwin. Okay? Which means, guys, I have now looked at circular motion in a very different way, and this helps me understand many different things. So, for example, if this is the path taken by a particle, and I draw many such circles like this, I can draw many such circles, even over here. Even over here, like this. The center of such a circle, I will also show the radius of such a circle. This C is called as the center of curvature. This R is called as the radius of curvature. How much curviness is there? Radius of curvature. And these circles, they are known as instantaneous instantaneous circles. Instantaneous circles. I hope this is absolutely very clear. Not just that, I can also see that the velocity at any given point is always going to be tangential. So the velocity is tangential. The velocity is tangential at every instant, at basically every instant. But for newer circles, obviously, when it goes from here to here, it is tangent to that new circle, etc. Also keep in mind, if by chance the path is a straight line, if it is a straight line path, then what should be the radius of curvature, or where is the instantaneous circle? Okay, no, my dear friend, I'm not from Kerala, but happy Onam. Yep, thank you so much. Happy Onam. You should teach me probably how to say happy Onam in Malayalam. Yes. Happy Onam to you. Yes. Thank you so much, guys. Yeah. So, when you have a straight line, then imagine there is no curviness. You can think as if the circle is very big, in fact, infinitely large. This is a small circle, then it becomes even bigger, then even bigger, then even bigger, then even bigger, then even bigger. So the more straight it becomes, the circle becomes larger and larger. That means the radius of curvature tends towards infinity. The radius of curvature tends towards infinity. Keep that in mind. Very good, Sanjay. Yes, Harborain. Excellent. So all these concepts, very, very important. Now, as a matter of fact, we also know that whenever, like say for example, even we take the example of projectile motion. Example, projectile motion, where the particle goes in a parabolic path, something maybe like this, okay, or it could be like this. So it depends on how much speed is there, what angle you projected, etc. So many things. At every instant, the velocity has different magnitudes, different directions, okay, different magnitudes, different directions, correct, something like this. But you will see the acceleration was always downwards, right? It was the acceleration which was always oriented downwards. So acceleration was like this. As you can see, the acceleration vector and the velocity vector can make any angle as the situation might demand. Over here it is obtuse, over here it is 90 degree, over here it is acute, which means in any 2D or 3D motion, velocity and acceleration can make any angle possible. This helps me understand many things now. Observe carefully. If I am taking an instantaneous circle, something like this, maybe this is the velocity at that moment. 100% the velocity has to be along the tangent. The acceleration need not be along the velocity. Keep that in mind. You can see acceleration can make any angle. It can be acute, it can be obtuse, it can be parallel, it can be 90 degrees, it can be anti-parallel. It can make any angle. But one thing is there, if acceleration makes an acute angle, then I can say for acute angles or basically 0 degrees, the speed increases. The speed basically increases. You can see that very, very clearly. But for obtuse angles, obtuse angles or 180 degrees, the speed reduces. And exactly at 90 degrees, what happens? When it is 90 degree, when it is basically 90 degree, the speed doesn't change. The speed basically doesn't change at that moment. The speed doesn't change at that moment. We know that the speed reduces, stops increasing. In fact, after that it starts increasing. So there is a moment where it is neither increasing nor decreasing, and that's exactly when the speed doesn't change. Yep. I hope this is clear. Yes. Right. Hi, Aerospace. Join in. You have not missed much. You can always replay whatever you have missed, even in the live class. So now think and tell me, acceleration can make any angle 100%. It can be here, it can be here. But I have a feeling out of option 1 and option 2, one of them is not possible for this given path. Which one do you think is correct? Which one do you think is wrong? Tell me out of 1 and 2. Acceleration, one of them is possible, another one is not possible. Which one do you think it is? Think about it, guys. If I'm turning like this, so my velocity is going or changing in this way, so acceleration can't be that side. It should be on the inner side of that circle only. So option number 2, yes, some of you probably got it, is not possible. It is only option number 1 which is possible. Yes, 2 is not possible. Correct. So this is how the acceleration must be. Remember, when the circle goes over here, and the velocity is over here, then the acceleration won't be this side. Then the acceleration must be on the side of the circle. Then the acceleration must be on the side of that particular circle. So that's how acceleration is always going to be. Like you can see, there is some angle made between the velocity and the acceleration. Now this acceleration will have 2 components. This acceleration will definitely have 2 components. One component is right over here. One component is basically right over here like this, and the other component probably over here. The other component right over here. These are the 2 components of the acceleration. One of the component is directed towards the center. The other component like you can see, is along the tangent, to that particular circle. That is why that component of acceleration along the tangent, which is along the tangent, is called as the tangential acceleration, or the tangential component of the acceleration. The one which is towards the center is also called as centripetal component, or the centripetal acceleration. Is that absolutely clear, my dear warriors? So centripetal acceleration and tangential acceleration, technically speaking, are not something new. Rather, they are just components of acceleration. So if I go back a little bit over here and I look at this projectile motion diagram, which is also a circular motion, which we just discussed, I can split this acceleration into 2 parts. One component over here and one component over here. This component will be the centripetal, along the velocity will be the tangential. Do you guys agree with this statement? Have you understood why I am saying so? Yeah, cos sign is one thing, but what is the name given to it? Centripetal and tangential. Did you understand it, my dear warriors? Why this is centripetal? Because the instantaneous circle will be somewhere over here. That is the reason why I am saying centripetal. Centripetal means something directed towards the center. As simple as that. Great. Very good. Now that you have come till this point, you will also appreciate one more thing. And that is, 1 second. Oops. If the centripetal acceleration is here, if this is the tangential acceleration, if this is the total acceleration, that means if there is acceleration, there must be force. If there is acceleration, there must be force. Remember that. So whatever is the direction of the acceleration, in the same direction, for this particular mass, whatever this mass is there, that mass, because it is accelerating, there must be a force. So the force must always be in the direction of the acceleration. So this is the net force. This F over here is the net force acting on the particle. That means this F is equal to our mass times our acceleration. This is your net force just by using Newton's law. Just like acceleration had component, even the net force will have components. One of the components, my dear warriors, will be here, and the other component will probably be here. Obviously, I by mistakenly put opposite. This was supposed to be AT and this was supposed to be AC, my bad. This component which is along the tangent, this will be the tangential force. This component of the net force will then be the centripetal force. So this is then called as your tangential force. Tangential force is the component of the net force along the tangent. Keep that in mind. Similarly, this is nothing but called as your centripetal force. Centripetal force is the component of the net force, along the center. I hope this is clear. This also means our tangential force and our centripetal force will be mass times the respective accelerations, m times AC or m times AT. As simple as that. Okay, I hope this is clear, my dear warriors. Okay, FC is mass times acceleration, FT is m times tangential acceleration, and net force is mass times net acceleration. Needless to say, again over here, that our this force vectorially as well as magnitude wise, how will it look? This net force is the vector combination of FC and FT, of course, but magnitude wise it is FC square plus FT square because they both are perpendicular to each other. Makes sense. The net force is the combination of centripetal force and tangential force together, and since both of them are perpendicular to each other, so this magnitude will be this square plus this square. Till this point, if everything is clear, give me a thumbs up. Till this point, if everything is clear. Any kind of acceleration or force is a vector quantity, Harborine. It's not scalar. So just because I'm giving it some name behind it does not mean it is a scalar. Whether it is tangential, centripetal, centrifugal, whatever, if it is a force, it is vector. If it is an acceleration, it is a vector. Names can come behind or ahead of it. These are like adjectives. Yeah? Okay. Great. Great. I hope this is absolutely clear. The same thing I can also say about this acceleration. This acceleration as a vector as well as the magnitude part of it. This acceleration is a vector combination of centripetal plus the tangential, and this magnitude wise it is AC square plus AT square. Okay, these are pretty much obvious. Okay, but still I'm blocking it for you. Okay, now out of these accelerations and forces, I have a feeling one of the component is responsible for changing the speed and one of the component is responsible for changing the direction. Let's have a look at the projectile motion and maybe we'll get an idea. Looking at this projectile motion, as you go up, you can see the speed is reducing. As you go down, the speed is increasing. At this point, the speed is neither changing, it's not increasing nor decreasing. So at this point, if it was not going up or down, that means the component of acceleration responsible for the speed is not there. Oh, so only centripetal is there, tangential is not there because the total acceleration vector is down. So there is no tangential over here. That means tangential is the one which is responsible for changing the speed. Correct? Yep, very good. Rotational mechanics will come later. Guys, concentrate on the class. Don't ask random questions now. Just concentrate on the class. You can keep asking me many questions. I can keep answering to you, but then the whole syllabus will be left over. Okay. So it is very clear that the tangential acceleration changes the speed, whereas the centripetal changes the direction. There are all kinds of possibilities where you might have centripetal, where you might not have centripetal, etc. Centripetal, tangential. Imagine both of them are 0. Imagine this is not 0, this is 0, this is 0, this is not 0. Both of them are not 0. Let's explore the possibilities, guys, whether these things can happen in real life. What do you think about each of them? Imagine both of them are 0. Neither centripetal is there nor tangential is there, which means the total acceleration itself is 0. The total acceleration itself is 0. Here, in all the other 3 cases, 100% there is some kind of acceleration, either centripetal or tangential, one of them. But since here the total acceleration only is 0, which means there is only one possibility. The particle is probably going in a straight line motion, or probably it is at rest. This is possible. So 100%, the first, I'll just put a tick mark because this is possible in real life. What about the second one? Yes, we'll be coming to the formulas also of centripetal and tangential in a bit. Yeah, both are possible, either at rest or in uniform motion. Nikhil will be coming to that derivation, that formula or that relationship in a bit. Hold on. What about this? Tangential is there, centripetal is not there. Think like this, centripetal changes what? Direction. Tangential changes what? Speed. So direction is changing, but speed isn't. Direction is changing, but speed isn't. So there is only one possibility, my dear warriors. Direction is changing, but speed is not changing. So basically, it is going in a uniform circular motion, like the hands of a clock or the moon going around the earth. Uniform circular motion. The fan rotating at a constant speed. The direction is continuously changing, but it is the speed which does not change. So speed is not changing, direction is. So 100% even this is possible. How about this? Direction is not changing, but speed is. Definitely this is possible, guys. Just consider one straight line motion or free fall motion. You drop something. Okay, first the speed is less, then it is even more, and then it is even more. So it is having speed changes because of tangential, but centripetal is not there. That means direction is not changing. So one-dimensional accelerated motion. So definitely even this is possible. What about this? Centripetal is also there, tangential is also there. Guys, I just showed it to you right over here, the case of projectile motion. Centripetal is there, tangential is there. Definitely it is possible. Projectile motion is an example, or even simple pendulum. A pendulum which goes back and forth. Speed is continuously changing. Stops, increases, stops. Direction is also changing. Once here, once there. Speed, direction is also changing of velocity, and so is the magnitude. So 100% this is possible. Best case example is of a pendulum which is going back and forth. A pendulum. Definitely this is possible. In fact, you can say a non-uniform circular motion. Non-uniform circular motion is the best example because the speed is continuously changing. In uniform circular motion, it is the speed which is remaining constant. So I hope, Nikhil, you understood. Everything is possible. Hi, Ragul. Is that clear? Center of mass, Rudreshwaran, October 1st week. Yep. So now that we understood the difference between centripetal and tangential, and also centripetal and tangential forces and how they are related to each other, let's see, are there any formulas for these accelerations? Let's see whether there are any formulas for these accelerations. Well, there are. So guys, talking about centripetal and tangential accelerations, this is tangential, this is centripetal, and this is the net acceleration. Strictly speaking, if the velocity is given to me, as a function of time, or if I know how it changes, then our total net acceleration, which is a bar, is simply given as just the derivative of velocity with respect to time, which is obvious, it has to be. It is nothing but rate of change of velocity. Rate of change of velocity. As simple as that. Makes sense? How quickly the velocity changes, that's acceleration. That's the definition of acceleration. What about the tangential acceleration? Observe this carefully. Tangential acceleration. Tangential acceleration, strictly speaking, 1 second. Tangential acceleration, AT, is, observe this very carefully, it is d by dt, but of modulus velocity. What is the difference between this and this? When I put modulus of velocity, that means magnitude of velocity. Magnitude of velocity, what is it? V bar is velocity. V bar is velocity. V bar modulus is nothing but speed. So, this is derivative of speed, means rate of change of speed. There are two different things, rate of change of velocity, rate of change of speed. I might be going with a constant speed, but my direction is changing, so still I am considered to be accelerating, even if my speed is not changing, because my direction changes and velocity is a vector. But if I truly talk about rate of change of speed, then that is tangential acceleration. Yep, I hope this is absolutely clear. But what if I put a vector symbol over here? What if I put a bar symbol over here? There is something which we need to do. This is now a scalar quantity, or rather the magnitude part of it. What is the direction of the tangential acceleration? Same as the velocity. Same along the velocity, guys. So hence, I will just put over here a symbol like v hat. So this part represents the magnitude. This part gives me the direction in the form of unit vector, like I cap, j cap, k cap. So which direction is it? I cap, j cap, in the direction of velocity, v cap. So this v cap will not change anything with magnitude, because unit vector means unity. So anything multiplied by unity preserves the magnitude. Keep that in mind. Is that clear? Lucky, I do remember you. Oh, welcome. Where are you now? This is tangential acceleration. Very, very interesting formula, guys. Okay, let me just block it out for all of you. This is net acceleration, of course. What about centripetal acceleration? Well, if the radius is given to you, then the centripetal acceleration formula is nothing but v squared, velocity square the velocity, and then divided by your radius, v square by r. But if you talk in terms of direction, then I am forced to put one negative sign and then put r hat over here. You might be wondering why this minus r hat. See, actually speaking, radius vector is like this. So this much part will be r hat. Centripetal acceleration is opposite to radius vector. That is why that negative sign. This is just showing the direction aspect of it. Magnitude wise, it is only v square by r. Magnitude wise, it is only this much. Magnitude wise, this is magnitude. Why is this minus sign? Because it is opposite to radius, towards the center. towards the center. That's all. But you will not use the minus sign otherwise. This one is the unit vector notation. Is this absolutely clear? V square by R is the magnitude for centripetal. dV by dt, but with V modulus is tangential, rate of change of speed. This is rate of change of velocity. So technically, this magnitude is nothing but rate of change of speed. Rate of change of speed. As simple as that. Rate of change of speed. Hari, you will be able to get my notes right over here. As you're watching this video, see this Jungle Book link, click on this link, log in, create your free account if it is not there. You will see a whole Excel sheet with my handwritten notes, DPPs, lecture links, and PYQs, everything, whatever is required is there. Okay, Hari Avinash? All right. Let's solve some questions. Ready for some questions, my dear students? Ready for some questions? Let's do some questions. Okay, put the fire emoji in the chat box quickly. I'm telling you that the position vector of a particle, is t square I cap minus, or let's say plus 4t cube j cap. 4t cube j cap. All right. Or let's just put t cube j cap. Now, and I will divide it by 3. Now, you have been asked to find the following things. Find velocity, acceleration, tangential acceleration, and centripetal acceleration. All of these things. Let's do this question, my dear warriors. How about this? Okay. I think polar coordinates are usually better, but depending on the problem type, like this one is rectangular coordinates, Cartesian coordinates. So we are doing it by Cartesian coordinates in this problem. It depends from problem to problem, how it is given accordingly, but polar are obviously easier. Now let's see how do we solve this question. The first few things are very, very simple, like velocity and acceleration. See guys, if I have to just find the velocity aspect, velocity is rate of change of position. So just take the derivative of it. So 2t divided by 2 I cap plus 3t square by 3 j cap. Therefore, our velocity will just become t I cap plus t square j cap. Okay. How about acceleration? That is also simple. Acceleration is just derivative of the velocity with respect to time. So derivative of t is 1. So 1 I cap. T square's derivative is 2t j cap. So basically our acceleration is just I cap plus 2 times t j cap. Okay. So this is done. What about tangential and centripetal? Let's look at the formulas. Tangential is rate of change of speed. Okay. I have to check the speed and then take the derivative of it. I have to take the modulus and then take the derivative of this. So look at this velocity over here. And let's try to figure out what is dv bar's modulus with respect to time. V bar is this. V modulus will be this component square, entire thing under the root, guys. So it will be derivative of this whole thing, which is t square plus t raised to 4. Did you understand why I did this? If this is V bar's modulus also, I can say, is nothing but root of x component square plus y component square. This is t raised to 4. So I've just taken the derivative of this. So this is a function of a function, guys. So you know this is going to go big now. So what happens is after this, which is just like saying this is t raised to 2 plus t raised to 4, whole thing raised to halves derivative. So first outer function's derivative, which is basically half into t raised to 2 plus t raised to 4 whole raised to half minus 1 is minus half into inner function's derivative. T square's derivative is 2t. T raised to 4's derivative is 4t cube. 2 can be taken out common, it cancels out. So it will become t plus 2t cube whole thing. This is negative power, so bring it downstairs. T square plus t raised to 4. I can take t square common outside and from numerator also t common. So 1 plus 2t square. From denominator, let me take t square outside the root, which will again become t, and I'll be left with 1 plus t square. T will cancel and I will be left with 1 plus 2t square upon 1 plus t square under the root. So this will become your rate of change of velocity. Speed. This will just become rate of change of speed. This is the magnitude of the tangential acceleration. I hope this is absolutely clear. I hope this is absolutely clear. Everybody fine till this point? Nikhil, see? Yep. Presently all going good, Lucky, very good, awesome. Now, this is only a small part of it. What about the tangential acceleration vector quantity? Remember, tangential acceleration as a vector quantity, I have to put v hat also. So, from this, I can easily find v hat. So, if you put v hat, that's it, you will get the answer. So, v hat will be, remember, vector divided by the magnitude of it. So, just take this and divide it with this. So, it will be t I cap plus t square j cap, whole thing divided by this magnitude. In this magnitude, remember, you can take t square common outside and it will become 1 plus t square. So t into root of 1 plus t square. T will cancel. So it will be I cap plus t j cap, whole thing divided by root of 1 plus t square. So from this, I will get the tangential acceleration. I will basically get the tangential acceleration. This is the magnitude, which is 1 plus 2t square upon root of 1 plus t square. Directional unit vector is this. So that will be I cap plus t j cap, whole thing divided by root of 1 plus t square. This into this, root cancels. So I'll be just left with 1 plus 2t square I cap plus I cap plus tj cap, the whole thing divided by 1 plus t square. That is your tangential acceleration. Is that clear what we just did? Give me a thumbs up if you understood it. Did you love this question? Yes, tangential acceleration is, oh, you can do that also. Yes, you can do that also. Yep. Now, over here, once I find tangential acceleration, how do I find centripetal? I'll go to that part also, just 1 second. But before that, let me tell you, there is an alternative way also to solve this. This is one way by finding rate of change of speed. Another way to do that is writing tangential acceleration as the acceleration's cos component. And think about it, why acceleration's cos component? If this is acceleration and this is our velocity, this is theta, obviously tangential acceleration is this one, which is a cos theta. Now a cos theta can be also written down as a cos theta into v divided by v. Why did I do this? Because I know I can use dot product. So I can do a bar dot v bar, whole thing divided by v, which is also a bar dot v hat. This will also give you the same answer. If you proceed ahead, you will get exactly the same answer as before, no change at all. This is an alternative way. Got it? Okay. Now, what about the centripetal part? Let's go to the last part, centripetal. I know one thing, centripetal plus tangential in the vector form is the total. Therefore, centripetal is acceleration minus the tangential. That's it, guys. So therefore, centripetal will be acceleration, which was found over here. Where is it? I cap plus 2t j cap. I cap plus 2t j cap. This is A minus tangential part. What was the tangential part? We got it here. 1 plus 2t square by 1 plus t square. 1 plus 2t square divided by 1 plus t square. Whole thing into what was it? I cap plus tj cap. I cap plus tj cap. Now you solve this, you will get the answer. I mean, I'm not doing it now over here. It will be very tedious, but I cap and I cap you subtract, j cap and j cap also you subtract, you will get the answer. But this is how you get it. So this is a proper advanced question, let me tell you. This is a proper advanced question. And I hope you enjoyed this question. Okay, Tony Stark, center of mass rotation, October 1st week. After circular motion, magnetism complete we'll be doing. Okay, the 12th standard syllabus, and then we'll be starting with center of mass rotation, October 1st week. By mid-October, rotation and everything will be done. SHM also, hopefully. And then waves will be done by October. Yeah, that's the target. Okay. Shall we go ahead? Shall we go ahead to another question, my dear students? Have you understood how these things work? How these things work? Lot of students try to do it very differently. You come to these parts at the end of the lecture or at the end of the chapter, but trust me, if you learn it this way, you will understand it better. Also remember, is centripetal force a new kind of force or tangential force a new kind of force like gravity, electrostatic, magnetic force? No, rather it is a component of a force. In fact, the net forces component it is. It is a component of the net force either along the center or along the tangent. So technically it is not a new kind of force. It's just some component, some mg is there. A component of mg might be centripetal or tangential. Keep that in mind. Okay. Now let's do one more question. And this is also going to be very interesting. Let's see if you guys can figure this out. Imagine for a normal projectile motion, where everything is given. Initial speed is given, theta is given, okay? Question is, find the radius of curvature. Find the radius of curvature at number 1, the start, number 2, at the top. Okay, these are the two questions. Find the radius of curvature at the beginning and exactly at the top. Let's try to solve this particular question. First of all, let me imagine the projectile motion. That will help me visualize a few things. Okay, this is how the projectile motion looks like. This is how my initial velocity looks like. At the topmost point, what is my velocity? It won't be the same. What's the velocity? Only the horizontal component remains. Remember it? So it will be u cos theta, of course. Acceleration due to gravity is always constant, no matter where you are. So here the acceleration is like this, correct? The acceleration is just going to be like this. And it is going to be g. Here also the acceleration is going to be the same and it is going to be g. Let's visualize some instantaneous circles so that you have some clarity over here. If I visualize an instantaneous circle right over here, maybe like this, and an instantaneous circle right over here, maybe like this. Things start becoming clear what exactly we need to do. This g is the total acceleration. Remember, this is your net acceleration. I think it will have two components. One of the component will be along the tangent. Another component will be towards the center. Here also, it will have two components, but the best part is since it is already perpendicular, this g is already the centripetal acceleration. This g is already centripetal. In fact, over here, the tangential component is a big fat 0. I need to figure out what is the centripetal and what is the tangential component. Okay, so let's figure that bit out. What is the centripetal and what is the tangential part? Till this point, everybody absolutely clear? Okay. Now observe this. Now observe this. See, let me just draw a horizontal line. Let me see. Okay, this angle is theta, guys. So this angle will be 90 minus theta. So then again, this angle will be theta. Correct? Theta 90 minus theta, theta 90 minus theta. That continues. Because this was 90 degrees, even this was 90 degrees, everything is 90 degrees. So every alternate angle will be theta, which means if this G was the net acceleration, this centripetal is the component which is close to theta. So that's why AC will be nothing but G cos theta and tangential will be G sine of theta. Do you guys agree? This is cos component because it is closer to theta. This component is far to the total, hence it is sine component. Here the centripetal is already given to be G. Now, once you do this, finding radius of curvature becomes easy. How? I'll tell you. Let's go back over here. Centripetal acceleration, what is the formula? V square by R. Centripetal acceleration. V square by R. I think I know most of the stuff over here. So let's do the first part over here. If I use this formula, centripetal acceleration is velocity square by radius. I will get the radius as velocity square divided by centripetal. So what is the velocity at this point? It is nothing but u. What is the centripetal at that point? It is basically G cos theta. So that's the radius of curvature in the first scenario. That's it. It's that simple once you figure out this diagram. What about the second part of the problem? Which is basically at the top. Again, guys, it's the same thing. The radius at the top will be velocity square by centripetal acceleration. Velocity at the topmost point is u cos theta. Centripetal is itself G. So hence the answer will be u square cos square theta whole thing divided by G. That's the radius of curvature. Got it? Clear? Absolutely. Everyone? And then ideas, if you are weak in physics numericals, solving only example questions will help you. Yes, example questions especially will help you, plus the class examples. See, often what happens in the books and in HC Verma, the examples might be at a little bit higher level. So you need to see some simpler solved examples, and that can come either through the teacher notes, your YouTube lectures or your coaching institute notes, okay, whatever the teacher is giving, and also in a way that you have understood it. So sometimes the solutions look complex or the order is not right. You are solving something but you need some data of some other chapter, other concept. So you need to plan it very properly. And PYQs probably towards the end you can do. Don't jump to PYQs immediately. HC Verma solved examples are really good level solved examples. They are not easy. Rather, you should go to some other books solved examples. And HC Verma short answer questions are good, and then probably you can go to solved examples because that will clear your concepts. Okay, great. So this is also done. Okay, let's see. If a particle going in a circular path of radius 2 meters is retarding at 4 meters per second square, or let's say 3 meters per second square, and and has a speed, let's say, of 2 root 2 meters per second. Question is, find number 1 tangential acceleration, number 2 centripetal acceleration, number 3 the total acceleration, number 4 the angle with velocity, the angle with the velocity. These are your questions. Let's try to solve this. Let's try to solve it. The particle is going in a circular path of some radius and is retarding at some rate and has some speed. Question is, what is the tangential, centripetal, total, as well as the angle made? So let's just imagine a circle for now. Okay, then let's just imagine the velocity over here, which is just given to be 2 root 2 meters per second. The radius is also given to me. The radius is also given to me. How much is it? It is basically 2 meters. Okay, perfect. This is the center. Now, this will have two kinds of acceleration. Obviously, one is centripetal, one is tangential. So, centripetal one will be like this. This is your centripetal. But be little careful over here. It is retarding, which means, will the tangential acceleration be this way or this way? Option 1 or option 2? Quickly think and tell me. Option 1 or option 2 for tangential? Think carefully. Think carefully. Which direction would the tangential be? Hi Sagar, welcome NN Ideas. I have a feeling it should be opposite because it is retarding. So it is not increasing the speed, it is changing it, but it is definitely reducing it. So hence the tangential acceleration would be like this, which means the net acceleration vector will be in this direction. So that is one big catch in this problem. Lot of students make some silly mistakes over here. Yep, be careful. Okay, so what's the centripetal acceleration? That is very, very straightforward. V square divided by R. What is velocity? Velocity is 2 root 2 square it divided by the radius. Radius is how much? 2 meters. Okay, 2 root 2 square is basically 8. 8 divided by 2, which is going to give me 4 meters per second square. That's your centripetal acceleration. Tangential is directly given to me. The magnitude of the tangential acceleration is 3 meters per second square. It's already given. It is already given. So you don't even have to calculate it. What about the total acceleration? Total acceleration is centripetal square plus tangential square under the root. Centripetal is 4, tangential is 3, 4 square 16, 9, 9 plus 16, 25, root of 25 is basically 5. So the total acceleration is 5 meters per second square. Total acceleration is 5 meters per second square. Is that clear, everyone, till this point? Okay, so this is done, this is done, this is also done. The moment you look at that diagram, one thing is clear. This is 5 units, tangential is 3 units, centripetal is basically 4 units. This only means one thing, this angle is 53 degrees. So this angle over here is basically 53 degrees, but that is not what the question is demanding. Angle with the velocity which the acceleration makes. This is the angle. So this theta, technically speaking, is 180 degrees minus 53. Did you understand? 180 minus 53, guys, which is 127 degrees. That's the angle. Many students make a mistake here also. Got it? Very good, Vijay. Yes, that's the answer now. Very good, Ashwin. Okay. Clear? Awesomeness. Let's go to the next question. Let's go to the next question. Here is the next question. If a particle, or let's say if a car moves along a circular track, moves along a circular track, increasing its speed, starting from rest, Many questions are there on this. Initial acceleration is making dash degrees or dash angle with the velocity. What angle is the initial acceleration making? Number 2, initially tangential acceleration is equal to or is not equal to 0, and centripetal acceleration is equal to or is not equal to 0. So you have to put is equal to or is not equal to. Number 3, the angle, or rather centripetal acceleration will dash increase or decrease, tangential acceleration will dash is increasing its speed starting from rest and maybe uniformly. This is mentioned. Okay. Last question, the angle between the total acceleration and velocity is dash, whether it is increasing or decreasing. Very nice question, proper JEE advanced type. Let's see if you guys can figure it out. If I'm making you feel that you're good at physics, that's good. That means you're loving it, and that's a good sign. Okay. How about the initial acceleration? What angle is it making with the velocity? Let's try to think. If it's starting from the rest, guys, okay, let me draw circular path right over here. Okay, maybe here it started. Maybe here it started, or maybe it started here. Slowly increase the speed even more, and so on and so forth. Here the speed is even more. Here the speed is even more, like this. Speed is slowly increasing. It started right from here. Where the velocity was 0. Now at that particular point, obviously it has to move ahead. So there must be some kind of tangential acceleration. It's not yet acquired velocity. V square by r will be 0. So centripetal acceleration which is there, centripetal acceleration which is v square by r, that will be 0 square divided by r, so that would be 0. Tangential acceleration would be there because it has to increase the speed. So initially tangential acceleration is definitely not 0. Centripetal acceleration is 0. This second part of the problem is easy to solve. From this we can solve this. Initially velocity is not there. Acceleration is totally along the tangent. What angle is it making with velocity? The answer is not applicable because velocity is itself 0. 0 does not have direction. You cannot find the angle with a vector which is a null vector. You can't find the angle with a vector which is a null vector. So hence the answer is not applicable because this is a null vector. This is a null vector. Velocity is a big fat 0. Many students put the answer as 0 degree. 0 degree is not correct. Got it, everyone? Anshuman? Yep. Common mistakes these are. Centripetal acceleration will dash, tangential will dash. The speed is increasing uniformly. That means it's the tangential acceleration which is remaining constant. So even here and even here or even here, it is the tangential acceleration which is constant. How do I know this? From this word. From this word. So here also tangential acceleration is constant. But speed is not. So v square by r will increase. So slowly this will be the centripetal. After some time even the centripetal acceleration will grow longer. So centripetal acceleration will definitely increase, but it is the tangential acceleration which will be constant in nature, which will be constant in nature. If you talk about the total acceleration now, here the total acceleration was like this. After some time you can see the total acceleration is like this. After some time you can see the total acceleration is like this. Initially it is making no angle with the tangent. Slowly the angle is increasing. Slowly the angle is increasing because centripetal component is increasing. So this light blue vector is moving more towards the center. So that's why the angle between acceleration and velocity is definitely increasing. Increasing. That is the answer. Got it? Everyone? Hi Lokesh. Such a nice question. These are proper advanced concepts which will help you both for mains and advanced. Cool. Shall we go ahead? Everyone? Till this point, everything clear? Yep. Okay. Let's go to the next question coming up on your screen, again on circular motion. This is a question about simple pendulum. This is a question about simple pendulum. Let's see if you can figure it out. In a simple pendulum, you have a light thread which is connected to a bob, meaning a pointed, thin, hardly any dimensions mass, and it keeps going to and fro. There is continuous to and fro motion, potential into kinetic, kinetic into potential. So that is what a simple pendulum does. These are the maximum angles which it can make. This is the time when it makes 0 degree. Sometimes this is also called as your average or mean position. This is called as your extreme positions. Right now this is extreme right. This is your extreme left position. This is your extreme left position. It starts from here, goes like this, stops, comes like this, stops, goes like this, stops, keeps going back and forth, back and forth. Can you tell me the speciality about extreme and mean positions in terms of the centripetal, the tangential accelerations, as well as comment about the velocity? What do you say about extreme positions and mean positions about with regards to centripetal, tangential and velocity, meaning whether it is 0, whether it is maximum, whether it is minimum, whether it is non-zero? What do you think it should be qualitatively? You can't give me the values, but can you tell me qualitatively whether it will be 0, non-zero, more, or minimum, maximum, etc.? Yes, Ansuman, for the previous one, the velocity will keep on changing. Yes, in fact, it is speed is increasing, right? It is increasing the speed. So velocity is definitely increasing in magnitude for the previous question. All right. So let's see how do we do this. I have a feeling when you reach at the extreme position, velocity only is 0. Think about it. When you reach at the extreme position, the velocity, the velocity is only 0. You come to rest for a moment. You come to rest for a moment. Velocity becomes 0 because direction changes. Direction definitely changes. You are going like this, now you are coming back. So for a moment you stop. So velocity is 0. If velocity is 0, centripetal acceleration, guys, v square by r, that will be also 0. V square by r, that will be 0. Do you guys agree with it? Yep. But what about tangential? I have a feeling if you go here, if you go over here, there is 100% mg force is there, mg force is there, tension force is there, centripetal is not there. Mg will have components, one component will be like this, other component will be like this. If this was your mg, this is your theta, this is also theta, this will be mg cos theta, this would be mg sin theta, there would be tension over here. Think about it, what is mg sin theta even doing over here? This mg sin theta is along the tangent to the path. It is along the tangent to the path, 100%. It must provide the necessary tangential acceleration. It must provide the necessary tangential acceleration. 100% it should be there. So I can also say at this extreme position, using force is mass into acceleration, force is mg sin theta, acceleration I do not know, cancels, so the tangential acceleration is g sin theta. So it is definitely not 0. In fact, it will be maximum because at this position theta is maximum, sin theta is maximum, so tangential acceleration will be maximum. Is that clear, everybody, till this point? How we have analyzed it? Okay. In this direction, along the straight line, along that thread, because there is no acceleration towards the center, shouldn't the tension balance out mg cos theta? Rather, I should say tension minus mg cos theta is mass into centripetal acceleration. Centripetal was 0, therefore tension is equal to mg's cos theta, exactly at the extreme position. Everybody fine? Okay. When you reach here, then your mg is downwards, tension is upwards. In fact, there is nobody to provide any kind of tangential force. If there is no tangential force, how will it even accelerate? Logically, it doesn't make sense. So there must be no tangential acceleration, so it is 0 because there is no tangential force. So that there is no tangential force at all. There is no tangential force at all. But since it is going in a circular path, there must be centripetal acceleration. Centripetal acceleration. In fact, using Newton's laws, net force is mass into acceleration. So I will say tension minus mg is m into AC. But if you want, you can also write this AC as v square by radius. Here radius is the length of the thread. Okay, what is v over here? The velocity is like this. In fact, at the bottommost point, this velocity is maximum since kinetic energy is maximum, potential energy is on the lowest side. Lowest potential energy, maximum kinetic energy. So velocity is not 0. In fact, it is maximum. Centripetal acceleration definitely existing. Definitely it is a non-zero vector. Did you understand this? Very, very nice concept. SK rules. Here, when you are at this particular position versus this particular position, what's the difference like? See, when you are like this is that mass. There is one tension force here, mg force here. There is nothing, right, in the horizontal direction. So along the tangent, there is nothing. So therefore, along the tangent, I would say the force is 0. The net force will be like this because the center is over here. So that's why tension will be more than mg. and tension minus mg is equal to mass times acceleration. That is Newton's second law. That is Newton's second law. Net force is mass into acceleration. Here what is happening? Mg is downwards. It will have two components, one here, one here. This is along the tangent, this is along the length. Can you see that? And since this is theta, even this is theta. So this will be mg cos, this would be mg sine. So only mg sine is responsible for the acceleration. Tension is even perpendicular. So nothing else is there. So mg sine theta is the tangential force. Okay. Mg sine theta is the tangential force, guys, which is giving the tangential acceleration. Is that clear? Yes, Namit, you can definitely watch the video. Now I have a very interesting question. At the mean position, can somebody tell me what or who is the centripetal force? I have asked this question many times to many students and I get very weird answers. I am asking you now, can you tell me at this mean position, who or what is the centripetal force at the mean location when this pendulum is going back and forth, back and forth? Think and tell me. At the extreme position, Ansuman, centripetal is not even there. Centripetal is not even there. Why? Because at the extreme, velocity is 0. Do not forget that. V squared by R. V only is 0. 0 square is 0. Divided with R, again 0. Tension is the centripetal force. Wrong. Answer is tension minus mg. This whole thing is the centripetal force. Got it? This whole thing is the centripetal force. So remember, centripetal force is not any new force. Don't show. Some people also show, sir, this is done, sir, centripetal force. FC. I have seen students doing that. They show centripetal force in the free body diagram. I hold my head. I'm like, when did I teach you like this? When did I show centripetal force acting as a separate force? It's not a separate force, number one. Number two, it's a name given to the component of the net force. Here, the net force is T minus mg, which is already along the radius. This is the radius of this big circle. So definitely T minus mg is the centripetal force. Tangential force is not even there. At this location, there is no centripetal force at all because tension and mg cancel out each other. The net centripetal force is 0. There is tangential force, which is mg's component along the tangent. So mg sine theta is the tangential force at the extreme position. Got it? Is this vertical circular motion? Yes, Ujjwal. And right at the beginning of the class, I told I do not distinguish between vertical circular motion, horizontal circular motion, then uniform circular motion, non-uniform circular motion. If you study it like that, it becomes a very confusing chapter. Rather, start off right from the top in this chapter. You know, okay, circular motion means anything which is going along a curved path. Whether it is an arc, circle, pendulum, projectile, all these are circular motions. Some are uniform, some are non-uniform. Yep. Yeah. Yes, and tension is not equal to mg. A lot of people make that another mistake. They write tension is equal to mg. How can tension be equal to mg? If tension is equal to mg, then it is not accelerating. Then there is no centripetal acceleration. So that is also not possible. So tension is not mg because it is already in motion. If velocity was not there, then it was a different story. So this is a very good example. Even this is a very good example. Even this, all these are very, very nice examples. What to tell? Now let's 1 second. Let's take an example of a car which is going on a curved track, and we know that if you increase the speed too much, you will end up slipping. We want to understand what's the maximum speed limit, number one. Number two, is there a way that I can go beyond the speed limit and not slip by doing something to the road? Number 3, if I'm able to do that, is it possible for me to reduce the wear and tear of the tires and make sure that the friction applied on the tires is as low as possible so that I have longer life of my tires? So we are basically going to study now, race tracks and some very interesting things about it, or in general how your roads are designed. Okay, all right. Rotational motion next month, because after this magnetism will start. So let's have a look, my dear warriors. Imagine there is a road like this. There is a road which is going like this, and then you have this beautiful little vehicle. And this beautiful little vehicle is going with some speed v, and this track itself has some radius which I am going to call it as r. Are you able to visualize this? This is like from some 3D angle from the top. You are seeing a road from the top and the car or that vehicle is going in this track. Okay, decrease the brush size, is it? Okay, if you say so, let's see what happens. I keep it big because then the handwriting comes out little bit better, that's all. If it is too small, then it is very faint, especially on the mobile screens, it might not look that great. Yeah. Now, in this process, let's see what are the different forces acting on it. Number 1, obviously its own weight will be there. So imagine mg will act down, something like this, the weight. Normal force from the wheels will act like this. If it is going at a constant speed, will there be any kind of tangential acceleration? Obviously no. So there is no tangential acceleration, it is basically going at a constant speed. So tangential acceleration is 0. But direction changes, but direction definitely changes. So centripetal acceleration is there. Centripetal acceleration is there. That means I should show something like this towards the center. Who will give the centripetal acceleration? Will normal give or mg give? Actually, normal is perpendicular and even mg is perpendicular to the centripetal acceleration. So none of them have any components. So there is only one person who can give that centripetal acceleration. Who is it? Friction. Exactly. Where will friction act? I have seen people say, sir, the friction acts like this. Okay. If friction acts like this, how the hell did it accelerate towards the center? Is there some ghost who is applying the force, pushing the car towards the center? So friction obviously can't act outward. The friction has to act. Some people even say, sir, sir, the friction is acting like this. If friction is like this, it is then perpendicular, so it can't give centripetal. So that is also not possible. The only possibility for the friction is to be like this. And is this friction static or kinetic? Many people say, sir, the car is moving, obviously it is static. The answer is no, it is actually static. There are multiple reasons for it. Number 1, the car is assumed to have rolling wheels. So you will, when study rolling motion, you will see the friction which is applied on those wheels is static in nature. Number 1, the vehicle is not skidding in any sense. Yes, the tires are rotating. Yes, the vehicle is moving, but the point of contact on the ground is at rest at every instant. Every instant a new point comes, becomes or has zero velocity before it lifts off, and a new point is in contact and again comes to rest. It is not even skidding outward. There is no lateral motion like this. No, it's not skidding. So when there is no skid, how can there be kinetic friction? So it must be static friction. It must be static in nature. Is this very, very clear? Yep. Now, that's it. That completes the FBD. So obviously in the vertical direction, normal force is equal to mg. In the horizontal direction, I can say centripetal force is equal to mass times centripetal acceleration. Centripetal force is the static friction, mass is mass, centripetal acceleration is v square divided by r. Now, once I look at this equation, I think, okay, fine, static friction is mv square by r. If I start increasing the speed, what will happen? Mass can't change, radius can't change, static friction will start increasing. But that's where the problem lies. If I am very adventurous and I'm increasing the speed, automatically static friction will start increasing. But remember, there is a limit till which static friction can increase. So that can only increase till Fs max. So speed will also have a limit. So in the limiting situation, in the limiting condition, so what is the limiting condition? When you increase the speed so much, static friction can't increase beyond that, you will reach basically Fs max is equal to m times, this is maximum velocity square divided by r. Fs max is mu into n. Normal, we just found it out, was nothing but mg. So this is m into v max square divided by r. cancels. So therefore, our v max will become root of mu rg. That is the answer. Mu rg. It is not drifting. Don't worry, it is not drifting. Correct. So this is a formula which again you should preferably remember. Is that clear, everyone? Now, with this comes a very interesting question. Imagine you are a race engineer. And you have to decide whether I should go on the inner track or outer track on a chicane, meaning a turn. Okay, so there are two lane options. This is lane number 1. This is lane number 1. This is lane number 2. You are allowed to push the car to as top speed as possible. So this is that turn you have to take. It starts here exactly and ends over here. Okay. This turn you have to take. You have inner lane and outer lane. You'll be like, sir, if I want to race, it's obvious, right? I will choose the shorter path length. But there is a problem. Can you tell me what is the problem in a shorter path length? What is the problem in a shorter path length? Nikhil, how to drift? You meet me, I will show you. I love to do all these adventure sports, especially on go-karts and everything. We should have a go-karting race. It's fun because I'm very aggressive. The problem is this R, the moment it goes down, the limit of the speed also reduces. So you might think, sir, I have to go less distance, this guy has to go more distance, I'll take the inner lane. The problem is, you can't accelerate beyond a point, you can't go beyond a speed limit because or else you will start skidding. The advantage for the person in the longer path is you can go at a higher speed. But then we do not know which effect will dominate. Did you understand? Maybe the person who is going on the outer track has so high speed that he is able to overcome the loss of time which he is encountering due to the extra distance. Or maybe the person inside, even though his speed might not be as much as the outer lane, but the shorter distance compensates for it. Got it? Isn't it amazing? Isn't it an amazing question? Okay, so what would you do? Tell me guys, will you go to the inner lane or outer lane? I want a war in the chat box right now. Inner lane or outer lane? What do you suggest? You are racing right now. This 180-degree turn is there. What will you be choosing? Assuming both of you have the same type of cars, whether inner or outer, maximum limits, you can push as much as possible, but you should not slip. So what do you think? What do you suggest? I have a feeling we have to calculate. There is no other way. This is physics, guys. You cannot guess. So let's try to see what will happen. Okay. If you have to calculate the time, obviously the time will be the distance divided by the maximum speed with which you will move without drifting. You want to make the time minimum as low as possible. The distance is basically nothing but the semicircle's perimeter, which is just going to be pi r. The maximum speed is nothing but root of mu rg, which we just calculated right over here. Going back over here, r will cancel, so I will have pi divided by root mu g, and over here root of r, that's the time. Can you see time is directly proportional to root of r? So if somebody is on a outer track, radius will be more for outer track. The time taken will also be more. So more time for the outer track. So this person will take more time, this person will take less time. So definitely this is what you will choose. Lot of you thought outer track is better, but actually this is the time which will be less, and this will be having more time. Got it? We have solved it using physics. Assuming you are pushing the car till the maximum limits. Just it is on the verge of slipping. Chaudhary, it is definitely enough, because it's not just 4 months. After that you get another attempt, and after that you have time for advance also. A lot of students do that. No way, sir, no way, but that is what physics says. There are some obvious assumptions here, like I'm pushing the car till the maximum limits, but in a real track what happens? They do something even more miraculous. So if this is the road, what they do, they neither take this nor they take this, rather they go like this, do a fast braking, and then they go like this, and then they start accelerating, and then they go like that. So they go in a very different approach. It's not even a proper circle. They practice years and years, and they just reach the extreme end so that you reach the maximum speed while accelerating. And when they are taking the biggest curve, biggest turn, that's when the speeds are lower. So they have hard braking, make a sharp turn, and then they accelerate with a longer radius. That's what they usually do. Okay, so it's neither this nor this in a real race. Keep that in mind. Interesting, isn't it? And I hope you guys are smashing the like button. If you have forgotten to do so, do it right away, right now. Many of you just watch the lectures, give no Guru Dakshina. Yeah, smash the like button quickly, subscribe to the channel. Yep. Now, the problem with this approach is that the speed is limited by mu. That means if the road conditions are not great, the tire has worn out, mu will be less. So my maximum limit will also reduce. So I want to not depend on friction. So what they do in reality is that the road itself is bent at an angle, meaning like this. This is called as a banked road. This is the cross-sectional view. This is called as a banked road. Very, very interesting theory. What happens in case of a banked road? Our vehicle is also slightly inclined, probably. Something like this, that's your vehicle. So it is also going in a curved path. You might have seen express highways, they are being tilted, or NASCAR racing, or the movie Cars, Pixar. So what happens is now the normal force is at an angle like this. This is how the normal force is. Okay. Then your mg force is obviously down, but mg force also will have some components. That's okay. So mg is right over here. And there is centripetal acceleration obviously towards the center. So maybe it is going in a radius like this. Right now over here, this is your radius. So centripetal acceleration is definitely there. Now what happens, the normal force has two components. That's the interesting part. The normal force will have two components. So our normal is now broken down into two parts. One component is over here and the other component is over here. If this was your normal force, if this is the angle at which you have tilted the rod, obviously this will also be theta. You can use geometry and you will see that even this particular angle is theta. Okay, so if this angle is theta, guys, obviously this will be n cos theta and this would be n sin theta. So you get the help of n sin theta component to provide the acceleration. Rather, you are not dependent so much on friction. If friction is there, good, but normal's component is providing the centripetal acceleration. Did you understand what is the benefit of it? Did you understand what is the benefit of it? Yes. So n sin theta is the added benefit, whereas over here, what is happening? You are completely dependent on friction to provide the acceleration. Now I will have a component. Now imagine, now there are two scenarios in this actually. One scenario is where you are going with as large speed as possible. So when you try to go with as large speed as possible, you will tend to fly, skid outwards. So friction will prevent you from slipping outwards by pulling you against the tendency to slip. Hence the actual friction will be, hence the actual friction will be like this. It will be like this. This is the direction of the friction. This friction will have two components. One component like this, which is Fs cos theta, and the other component will be like this, which is Fs sin theta. These will be the two components, guys. See if you are able to visualize this. It is preventing you from slipping outwards by pulling you down like this. Is that clear? Why friction acts down? So actually now there are two forces who are providing the centripetal acceleration. If I ask you, who is the centripetal force? Come on, put it up in the chat box, my dear warriors. Who is the centripetal force? What will your answer be? Sir, the centripetal force is n sin theta and Fs cos theta together. It is both of them together which is providing the necessary centripetal acceleration. Yeah, both of them together. Correct. Awesome. Great. This is possible when you are going with very large speed. So when you are trying to find maximum speed, this is what you will do. But imagine friction is not acting only, and you are driving carefully at that speed. That is called as optimum speed. Optimum speed, and that's when friction is absent. Friction is absent. Not just that, there will be very less wear and tear. That is why it is called as optimum speed, because hardly any wear and tear of the tires. These are the two most important cases, free body diagram, for a vehicle going on a banked road. Now, equation wise, it is very straightforward. This normal and this mg, you can start solving this. I mean, it's just components which you have to balance. But usually what they do, rather than splitting normal and friction, they split acceleration and then they solve the question. That is also going to give you the same answer. But I'll just tell you what will the equations look like in this scenario. N cos theta is upwards, is being balanced by friction and mg. Fs, sin theta minus mg. This is equal to 0. In this direction, normal sin theta normal sine theta plus friction cos theta is equal to mass times centripetal acceleration. Okay, this together is your centripetal force. This together is your centripetal force. Now do not forget, static friction in the limiting case will be mu into n. So solving these equations, finally you get the answer as follows, which is for the maximum speed. V maximum is equal to root of Rg. This is after solving. V max is equal to root of radius times gravity. You get mu plus tan theta upon 1 minus mu tan theta. This is the final answer that you get after solving this. Remember, centripetal acceleration itself is v square by r. So the root comes because the velocity was squared. Eventually you take square root on the end formula. Now the thing is, this formula looks complex, but you can also simplify it if you wish to. And I'll tell you the easier way to remember this formula. Do you remember angle of repose? Do you remember angle of repose? That concept. Angle of repose, the minimum angle after which a body tends to slide on an inclined plane. Angle of repose, the formula was tan of alpha was mu. So instead of mu, just put tan alpha plus tan theta upon 1 minus tan alpha tan theta. This looks like tan A plus B formula. This looks like tan A plus B formula. So actually speaking, this can be reduced to a simple looking formula, which is Rg tan alpha plus theta. That's it. What is alpha? Alpha is your angle of repose. Theta is the actual angle of banking. Theta is the actual angle of banking. This was your angle of banking of that particular road. So this is a much easier looking formula, I suggest. Rg tan theta plus alpha. If you notice, the previous formula is also the same thing, because mu technically is nothing but tan alpha. So it is also Rg tan alpha, but theta being 0. Rg tan alpha, but theta being 0. Think about it. If theta is absent, what will happen? It will become Rg tan alpha. Tan alpha is mu. So it is mu Rg. It's one and the same thing, guys. Got it? Very nice questions. Okay. Now for optimum speed, like I said, friction is absent. So if friction is absent, everywhere that mu will not be there. Mu will not be there, guys. Mu is 0. So you'll just get Rg tan theta. Forget mu. Friction is not there. So what's the formula that you will get? You will just get optimum speed. Optimum speed is root of Rg tan theta. That's all. That's your optimum speed. Is that clear? Yep. What is the circle for centripetal acceleration? That circle is in the horizontal plane. You have to visualize it like this. It's like that. This is that circle. The circle is not like this. Many people think the circle is like this. No. Visualize a circular track like this. Okay, are you able to visualize this? Just imagine a circular track like this. It's slightly lifted from the bottom. Okay, this is one circle. Just imagine another circle over it. Parallel horizontal plane. Cool? Questions are very simple, Kushal Kohli. It's not that difficult. You directly get numerical based substitution questions. Is tan alpha containing is similar to like tan theta? Sir, is tan alpha contains an angle similar like tan theta? But theta and alpha mean completely different things. Don't get confused. Theta represents a physical angle at which you can see the road. You are seeing the road banked at that. Alpha is the angle of banking. Alpha is the angle of repose. So say for example, I tell you, listen, there is a question like this. The radius of a road is, let's say, 10 meters. Okay. The coefficient of friction, let's say, is, I don't know, maybe let's take it as 37 degrees maybe. Coefficient of friction is 37 degrees. The angle of banking is, let's say, 30 degrees. Or let's do one thing. First, maximum speed limit for unbanked road. Number 2, optimum and maximum speed for road which is banked at 53 degrees. That's the question. For a road which is banked at 53 degrees. Very, very nice question. Let's try to solve this part by part. Let's do the first part. Maximum speed limit for unbanked road. Unbanked means there is no inclination. It is directly flat, just like this diagram right over here. This is an unbanked road, and we found the answer to be root mu rg. So let's try to solve this. So for the first part, V maximum is root mu rg. Mu is given, oh sorry, why did I write mu as 37 degrees, guys? Angle of repose, sorry, my bad. So it's supposed to be not mu. Alpha, so sorry. Alpha is 37 degrees. That's what I meant. So what will be mu then? Mu will be tan of alpha. So tan of 37, tan 37 is 3 by 4. So mu is basically 3 by 4. Radius is basically 10. G is also basically 10. 10 and 10, 4 square roots proper. So 10 by 2 root 3. That means it is 5 root 3 meters per second. That's the first answer. Everybody till this point clear? 5 root 3. Understood? Clear? Good evening, Usha. Okay. Now, second part of the question, let's solve optimum speed first. The optimum speed formula is root rg tan theta. Radius is basically 10. G 10. Tan 53. Tan 53 is 4 by 3. Tan 53 is 4 by 3. 10, 10, 100, 100's root is 10. 4's root is 2. And I will be left with 1 by root 3. So this answer will be 20 by root 3 meters per second. That is for optimum speed. Alpha, the angle at which the car won't skid down, till which the car won't skid down. Any angle beyond that, it will skid down. I'll come to that. There is a very interesting learning also from this problem. The maximum speed formula is root of rg tan theta plus alpha. Now what is it? R is 10, G is 10, tan theta plus alpha 53 and 37. So 53 plus 37. Guys, 10's root is 10. Root tan 90. Guys, this answer is tending towards infinity. Infinity. You know what we have done now? Because the answer comes infinity. It's a very, very interesting thing. Can you tell me what is happening in this question? Answer came out to be infinity. It means no matter what you do, however high your speed is, this car won't slide. So it won't slide for any large speeds. It won't. This is very, very interesting design, the values which I have chosen. No, it won't fall down. But there is a problem. There is a big but. What is that big but? 53 and 37. If you see, guys, theta value is more than alpha, which is 53 degrees is obviously more than 37 degrees. Which means if by chance something happens, the driver is like, okay, wait, I'll take a break. Let me stop the car. If he by chance parks the car, the angle of inclination is more than the repose, so the car will slip. So if he stops, it will slide. Isn't this crazy? You have to keep moving. If you don't move, gone, the car will slide down. Crazy, right? And best part is there is no upper limit to it, but there is a lower limit. You can't stop the car. This is one of the best questions that you can find. And JEE can trick you with such things. Many people will think something is wrong. How can theta be more than alpha and all such things? But yeah, it can happen. It's just you're making it like that. You generally don't want it to be like that. But in this problem, it has been designed in that way. There is no upper limit, but there is a lower end. If you try to go at very low speeds or stop, that's it, the car will begin to slide. Did you love this question? And if you loved this question, quickly smash the like button right away, right now. Yep, do that. Done? Dusted? Can we go ahead to the next question, guys? Can we go ahead to the next question? Okay, great. So we have done these questions, banked road questions actually. So this is done. Okay, this is also done. Now there comes a question where you have a pendulum and you want it to complete a circular path in the vertical plane. But the problem is, for a pendulum, is the string. String can be pulled, but you can never push a string. It doesn't make sense. If I have a string, how can I push it? I can only pull it, right? It makes sense. Like for example, I can just show you with this charging cable right over here, without hopefully breaking it. I can pull this. Obviously, there is a tension. If I pull it more tension. But if I push it, it becomes slack. This is a slack string. So imagine there is something which is, forget this part. Imagine something which is hanging. If it goes like this, it will obviously be under tension. But imagine it starts going up. There is a good chance it will become slack and it will fall down. So as the mass is given enough velocity, and when it goes up, it might become slack and it will fall down. And those chances are more once it crosses this 90 degree mark, that is, it becomes horizontal. This is 0 degree, 10 degree, 20, 30, 40, 50, 60, 70, 80, 90. After 90, if it does not have enough speed, if it stops, that's it. It will become slack and it will fall down. If it is given slightly more speed, it will go till here and maybe fall down. If it is given even more speed, probably it will go till here and maybe fall down. But you want it to complete circular motion means you have to give it enough speed so that it goes till here and it has enough speed. Tension should be there. It should not become slack, and tension should be preserved at the topmost point. Once it crosses the topmost point freely, smoothly, that's it. It will again continue its journey and it will be able to complete the circular motion. Are you able to visualize this much? Are you able to visualize this much vertical circular motion? So the critical aspect of a vertical circular motion happens at the topmost point. That's where if the string does not become slack, you are able to sustain the journey at the topmost point, which means you will be able to do it anywhere else also. Okay. So let's see a vertical motion of a pendulum. Vertical motion of pendulum, which we have already done partly right over here. If you remember, some aspects we studied right over here, but now we are completing the entire circle So here we have a pendulum which is going in a complete circular path like this. This is one place, this is another place. The most critical aspect is over here. This is the length of the pendulum. This is the length of the pendulum, this is the center. This is that mass. What are the different forces acting on it? One, obviously its own weight, mg. Second is basically the tension in the rope. And lastly, do not forget, there is also some velocity over here. This is at the top. At this point, there is no tangential acceleration, there is only centripetal acceleration. So centripetal acceleration is obviously directed towards the center like this. So using Newton's law, I would just say the net force towards the center is mass into centripetal acceleration. The forces acting towards the center are mg and tension. So that will be equal to mv square by L. Radius is the length over here. Now observe carefully. If I reduce the speed, what will change on the left hand side? Quickly think and tell me. If I go with a lower speed on the top, just think about it. This was our pendulum, this was our pendulum. I am reaching the top. If I go with lower speed on the top, what will reduce? Weight can't reduce. M is constant, G is constant. Tension will reduce. Yes, tension will reduce. So the tension will begin to reduce. But there is a lower limit to the tension. That means there is a lower limit of the velocity. Tension can't be lower than 0. It can't be lower than 0. That's when the velocity is minimum, which is then the critical state. So then when the critical state approaches, mg is equal to mv minimum square by L. Mass cancels and the minimum velocity at the top comes out to be root of GL. Very important formula again. The velocity is nothing but root of GL. Is that absolutely clear, my dear warriors? This is the velocity at the top. Velocity at the top, which you should have. Anything more than this is okay. Anything less than this, the string will become slack. You will not be able to complete it. But usually what happens, you are not interested in the speed at the top alone. You will be like, sir, I hit something, sir, and it has to go in a complete circular path. I have hit something, sir. It has to go in a complete circular path, and I have hit it at the bottom. So usually you will be interested in what is the minimum speed at the bottom. What is the minimum speed at the bottom? Okay. So how do I find that? I think I'll use energy conservation. I'll just say, hey, listen, initial kinetic energy at the bottom plus the gravitational potential energy at the bottom is equal to final kinetic energy at the top plus potential energy at the top, gravity. What is the kinetic energy at the bottom? Half m, this velocity at the bottom, square. Potential energy, 0. I'll take this as 0 line. At the top, what is the kinetic energy? Half m. Velocity is root GL, do not forget, because that is the bare minimum speed you need. So root GL whole square. Gravity wise potential energy, I've gone from this point to this point. What is the height difference? L plus L. It's the diameter. So it is mg2L. Is that absolutely clear? It is mg2L. Great. So let's proceed ahead and see what happens. MMM cancels. Okay, perfect. And I'll multiply the entire equation with 2. So velocity at the bottom square is equal to, if I multiply by 2, 2 cancels out. M also has gone. So I will have GL over here, root cancels. M has gone. 2 2s are 4 plus 4GL. GL plus 4GL, 5GL. So velocity at the bottom is basically bare minimum root 5GL. That is the answer. Bare minimum, you need this much speed at the bottom. Got it, everyone? Very nice. This also works for something called as a death well, where, or you might have seen those racetracks, Lego or I don't know, Hot Wheels, where you have a track like this and it goes like that and goes like this. Have you seen that? You know, probably your cars go like this, Hot Wheels track. Yep, everyone. And there is some, hold on. You start the journey from here. This is a completely smooth track and this vehicle goes like this, increases the speed. After reaching here, it goes like that and then comes out from here. Correct? I'm pretty sure you would have seen such stunts being performed like this. It goes from here like this, goes till the top, again comes back and returns back over here and goes over here. I'm pretty sure you would have seen this. So the question is, what's that height which is required, bare minimum, so that it is able to complete the circular motion? What is the height which is required, bare minimum, so that it completes the circular motion? This problem is just like this problem, just that instead of tension, you have normal. And it should not, that car should not leave the surface, means the normal should not become zero, or else the contact will be lost. So the same free body diagram, same formula, same technique works. So this problem, I say, is just like pendulum. It is just like the pendulum question. It is just like the pendulum question. Okay, there is no difference at all. So which means at the bottom, I know what the speed should be. The velocity at the bottom must be basically root of 5gr. How will you get this speed? From the potential energy. So the potential energy converts into kinetic energy. Potential energy is mgh. Kinetic energy is half m velocity at the bottom square. M will cancel. Gh and that 2 will make it. Velocity at the bottom is root 5gr whole square. So when you square it, you will get 2gh is equal to 5gr. Gg cancels, so 2h is equal to 5r. Therefore, h is equal to 5 by 2 times of r. This is the minimum height at which you should release this mass, so that when it reaches here, it has enough speed to complete the circle and go on that side. Got it, my dear warriors? Such a nice question. Now, this is okay if the pendulum is made of thread or rope. The pendulum is made of a rope or basically a thread. The problem, or rather the simplification, happens when it is not a thread or a rope. It's a vertical pendulum. It's a vertical pendulum, but it is made of a light rod. It is made of a light rod. You'll be like, sir, what difference does it make? It definitely makes a difference, and you will see why. Imagine this is your circular path. This is at your topmost point. This is the radius. This is the center. A rod like this pen, I can pull it, I can push it, nothing happens. Nothing happens. It does not buckle, it does not bend, it does not become slack. So when you have a rod, this doesn't become slack. So that's the good thing. If it doesn't become slack, that means I can give it bare minimum velocity. You give it such low velocity, here the limit was, this tension can't go below 0. I mean, that's the least possible thing you can do. But this rod, it can undergo compression, it can undergo tension, there is no harm in it. So this velocity at the topmost point can be as good as 0. Just more than 0 or just very close to 0, but more than 0, it's enough. It will be able to go on the other side, which means this is much lesser than the before one. Remember, here the minimum speed was root GL, here the minimum speed is 0. So obviously at the bottom point, the velocity will also be slightly lower because you don't have to reach that much speed. You can again apply kinetic energy at the bottom plus potential energy at the bottom is kinetic energy at the top plus potential energy at the top by conserving energy. At the bottom, kinetic energy is half m v bottom square, potential energy is 0, I'll take that as 0. At the top, it is 0 kinetic energy because negligible speed. Gravity wise, I have gone the diameter's height, so it will be mg2r. M and m gets cancelled. V bot square by 2 is equal to 2gr. 2 into 2 is 4. So velocity at the bottom will be root 4gr. This is definitely lower than root 5gr. So definitely it is less than that. Keep that in mind. Okay, because you need not as much speed as before. Is that clear? The difference between a rod and a string or this track kind of questions. So track or rope, use root 5 gr and root gr. Rod is there, 0 and root 4 gr. Those are the values. I miss you. Why do you miss me? I'm here only. Where have I gone? No. We'll take a break later on. Okay? Clear? Yes. Now that we have completed most of the concepts of centripetal and tangential forces, etc., let's slowly introduce some angular terms and the final concept of centrifugal force. Okay? Let's do that. Ashwin, I'm not sure, bacha, so I can't guarantee, but we'll try to complete as much as possible, and whatever chapters, even if it is remaining, we'll try to cover it in the crash course, or we'll have the final revision rounds, right? One shots. In that we'll try to complete it. Don't worry, right? So at least our high weighted chapter should be completed. At least those chapters which give us 99 percentile should be completed. So let's do that first. Okay. All right. Now, yes, some of the angular terms. Let's learn them. Okay. In one dimension or two dimension, we started off with position, that is the coordinate, then displacement, then what's the velocity, how quickly you are displacing, and then how quickly you are changing that velocity, which led us to acceleration. In rotation or circular motion, you also have the same kind of terms. So usually we use the polar coordinates because that is generally easier, and to refer the position of any particle in a circular path. So let's say, for example, right now a particle is here, and after some time maybe the particle reaches here. This is at t, this is at t is equal to 0. This can be called as theta naught. This in general can be called as theta. This theta represents your angular position of that particle in that circular path. As time progresses, the theta will change, and it is very easy to locate the particle in terms of theta. I'll just tell you, angle is 40 degrees or 50 degrees or 100 degrees or 200 degrees, you know where you are on that circle, and if you know the radius, of course. Whereas theta naught can be called as the initial angular position. Just like you had position, you have angular position. So then you get this term called as angular displacement. Angular displacement. And this angular displacement, delta theta, is nothing but exactly what it should be. It is the final position minus the original position. That's it. That is your angular displacement in simple terms. So if I had to mark angular displacement over here, this much would be the angular displacement. Is that absolutely clear, everyone? Yep. Now I'll give you some examples and you will tell me what's the angular displacement in each and every case. A particle starts from here, goes like this and stops here. What is angular displacement? A particle starts from here, goes like this and comes over here. What's the angular displacement? A particle starts from here, completes one rotation, and then the second rotation and stops over here. What's the angular displacement? A particle starts from here, completes one rotation, but decides to take a U-turn, and goes like this and comes and stops over here. What's the angular displacement in this case? First one, very simple. It's 180 degree or pi radian. Everyone, pi radian, very simple. Okay, what about the second one? I'm not talking about displacement. See, displacement is different than angular displacement. If the question was displacement, then the answer will be 2r. Then the answer will be 2 times of the radius. This would be just the displacement. Angular displacement is the angle covered, which is pi radian. Here you have come back to the same point, displacement is 0. Here also you have come back to the same point, displacement is 0. Here also you have come back to the same point, displacement is 0. But I don't feel angular displacement is 0. Angle wise, how much I have displaced? I have covered 360 degrees or basically 2 pi radians. Even though my displacement is 0, angle wise I have moved 2 times. So it is 2 times 360, 720 degrees or basically 4 pi radians. Do you guys agree with it? Understood the difference between just displacement and angular displacement? Yep. So 1 rotation and 2 rotations. Okay, 1 and then 2. So 2 into 2 pi is 4 pi. Here went like this and came back. So I wound and unwound. So the angular displacement is 0 radian. So 0 radian angular displacement happens when you go and come back. Not just you go and reach the same place. It's slightly different the way it works than displacement. Got it? This should clear your concept. Awesomeness. So this is done. Let's go to the next part. So I move from a place to the next place. I move some angle over here. This was my angular displacement. There is a term called as what is my angular velocity? Omega. Angular velocity. Angular velocity. And this is my angular displacement. Angular velocity is nothing but angular displacement upon the time taken. The unit obviously will be radian per second. Just like you had meters per second, this is how many radians you cover per second. Average angular velocity, this is average, is the total angle which you cover, is nothing but the total angle which you cover upon the time taken. So it is delta theta by delta t. But when you talk about instantaneous angular velocity, instantaneous, then that theta displacement is very less, so it will just become d theta divided by dt. This is instantaneous, this is average, just like you have v is dx by dt or delta x by delta t, depending on whether you are finding average or instantaneous. This was for average, this is obviously for instantaneous. Is that absolutely clear? Now, is omega somehow related to the velocity which is along the tangent? The answer is yes. This velocity which is there along the tangent is definitely related to this omega. Okay, and how is it related? Let me tell you. See guys, if you ask me what is the length of the arc over there, I will say it is radius times the theta. The length of the arc is nothing but radius times the theta. What if I divide this with time? I divide this also with time. This arc distance upon time will give me just the velocity. Do you guys agree with it? It will just give me the velocity. R is R only. R is the radius of that circle. What is angle covered per unit time? It is nothing but angular velocity. So V is equal to R into omega is a formula which you should know. More the velocity, more is the angular velocity. That's it. Clear? Understood? Now, with this transformation, V is equal to R omega, if you go back little bit in time and you go to the formula of centripetal acceleration, the magnitude specially. Centripetal acceleration, the magnitude was V square divided by R, isn't it? How about writing velocity as R omega and then whole square divided by R? So it will become R square omega square divided by R. One of the R gets cancelled and you will get the centripetal acceleration as omega square R. That is also a formula. Omega square R or V square by R, one and the same thing. Just by substituting velocity as R omega. Got it, everyone? Okay, so that was that one over here. Next. Imagine my velocity is also not constant. Here my velocity was omega I, omega initial. After some time my velocity changed to omega final in some time. So then what you get is a term called as angular acceleration. Just like you had velocity, then you go to angular velocity, then angular acceleration. So you have this term called as angular acceleration. Symbol is alpha, which is how much is the change in angular velocity. How much did the angular velocity change by? Whole thing divided by the time which you take for it. Whole thing divided by the time taken. So again, the unit wise, if you see, radian per second, so it will just become radians per second square. So you start off with the average definition first. Average angular velocity will be nothing but your delta omega by delta t, change upon the time taken. But if you put d omega and if you put dt over here, what you get is instantaneous angular acceleration. This is average angular acceleration. This is average angular acceleration, and this was your instantaneous angular acceleration. Rate of change of angular velocity. Is this clear, everyone? I'm so glad, Adesh, you got very good marks and you loved it. Super clear, very good. And I hope you continue the ROAR series and continue getting more good marks in every chapter. Okay. Completion Pirate, I have already done integration for basic physics, mathematics. Okay. In the first few lectures, just check it out. It's there in the playlist. Yep. Dynamics. What dynamics, Haswant? We started off with dynamics of circular motion right from the beginning. That's what I told you. Okay, I will be doing this chapter a bit differently. Once I did acceleration, I told you, listen, force. We started off with dynamics right from the beginning. We didn't take it separately. It was done together, everywhere. Everywhere. We were doing dynamics all together. Yep. Great. So this is also done. Now, you might be wondering, sir, if there is so much of resemblance in linear motion and rotational motion, will there be something called as kinematics of circular motion, where you have some initial angular velocity and after some time you get some new angular velocity, and maybe during this time there was some angular acceleration which was constant, and maybe, sir, that you might also find something like your angular displacement. Maybe you have something like angular displacement over here. Is this there? The answer is yes. So you also have something called as the kinematics of circular motion. Kinematics of circular motion. This kinematic equations of circular motion is only valid under one scenario, that is angular acceleration is constant. Only then all the equations are valid. What are the equations going to look like? Final angular velocity is initial angular velocity plus alpha into time. V is u plus at. Similarly, instead of displacement, you have angular displacement is equal to initial angular velocity into time plus your half alpha into t square. This is also valid. Lastly, final angular velocity square is initial angular velocity square plus 2 into alpha into delta theta. These equations are even valid over here, as long as the total acceleration is a constant. That is why I have highlighted this over here. Clear, everyone? Till this point? Sir, will you teach banking of roads? Haswant Kumar, I already did that. I think you missed that part. It's already done, bacha. Banking of roads, banked roads, optimum speed, questions on that, already done. Okay, let's take up some questions. Even displacement in n second is valid. Yeah, displacement in n second is valid. Yeah. Okay, so let's say there is a question like this. If a fan rotating at 120 RPM increases the speed to 360 RPM in 3 seconds. Find number 1, angular acceleration, number 2, number of rotations. This is the question. Let's try to solve it. Let's see what is given to us before we begin the problem. First information is initial angular speed, which is given to be 120 rounds per minute. How do I convert rounds per minute into radians per second? You might wonder. Think. 1 round is 2 pi radians. So if there are 120 rounds, and that too in a minute, each round being 2 pi radian and each minute being 60 seconds, you multiply by 2 pi, divide by 60, 60 goes with 122 times 2 into 2 pi is basically 4 pi. So the answer is 4 pi radians per second is the original speed. What about the final speed? Same logic. It is 360 rounds. Round is 2 pi radian. A minute is 60 seconds. 60 goes with 360 6 times. And 6 into 2 is 12. So it will become 12 pi radian per second. Time is also given to you. Time is given to be 3 seconds. So this was final. Time is also given. Okay. So let's find average angular acceleration first. How do I find that? Alpha is delta omega by t, delta t. Or you can also use V final is V initial plus alpha t. That's also okay. This is the same thing if you rearrange the equation. Alpha into t. Final is nothing but how much? 12 pi. So this is 12 pi. Initial is how much? 4 pi. Okay. Alpha, I don't know. Time, 3. Okay. So therefore, 3 alpha will be 12 pi minus 4 pi, which is basically 8 pi. Is that right? Correct. So how much will it be? Yep. Alpha will be nothing but 8 pi by 3. I don't know why it acts weird at times, the screen. Okay, 8 pi by 3 radian per second square. Clear, everyone? Next, what about number of rotations? I think we should use final velocity square, initial velocity square and all of that. So let's see. Final velocity square is initial velocity square plus 2 alpha delta theta. So final is nothing but 12 pi. So 12 pi whole square is equal to initial velocity is nothing but 4 pi. So 4 pi whole square plus 2 into alpha is 8 pi by 3. Keep answers in pi, it's okay. Don't have to convert it into decimal. I was just seeing some of you commenting in the chats in decimal. That's okay. Fine. This will be nothing but 144 pi square. 4 square is 16, so 16 pi square is equal to 8 2s are 16 pi by 3 into delta theta. Obviously, few things just get cancelled, like this pi over here, this pi over here, and this pi over here. Is that right? Everyone? Till this point? Clear? What next? Come on. What next, guys? 16, 16, 16 also you can cancel. 16, 16, and here it will go 9 times. Okay, so the equation will come down to 9 pi minus pi is equal to 16 and pi have gone delta theta by 3. 9 pi minus pi is basically 8 pi. So delta theta is basically 24 pi radians. 24 pi radians. But don't give the answer in radian. The question is number of rotation. Each rotation is 2 pi radians. So the number of rotation is the angle divided by 2 pi. So 24 pi divided by 2 pi. So it will be 12 rotations. So the total number of rotations is basically 12 in number. Yes, got it? That is how you solve these kind of questions using kinematics. Let's do one more question, guys. Next question on your screen, here it is. The question goes like this. Imagine theta is given as t square minus 2t plus t cube radians. Question is, find instantaneous angular velocity and angular acceleration at t is equal to 2 seconds. Number 1. Number 2, find the average angular velocity in 2 seconds. These are the two questions. Find instantaneous and then find the average. Okay, first one is both for omega and alpha, and the next one is only for average angular velocity. Let's try this out. Omega and alpha. Theta is a function of time. Do I know some formula? Let's go back. If you notice over here, omega is the derivative of theta and alpha is derivative of omega. That should give you the hint. Okay, so it is a question involving derivatives, nothing more. So omega being d theta divided by dt, just have to take the derivative of t square minus 2t plus t cube. So t square's derivative 2t, 2t's derivative 2, t cube's derivative 3t square. That's it. That is omega. Okay. Similarly, alpha will be d omega by dt. So take the derivative of 2t minus 2 plus 3t square. Therefore, alpha will be 2t's derivative is 2. 2 is a constant, so derivative is 0 plus 3 multiplied by 2t. Hence, it will be 6t plus 2 radians per second square. This was radian per second. But the question is at 2 seconds. So let's do that. So at t is equal to 2, angular velocity will be, put time as 2 over here. 2 multiplied by 2 minus 2 plus 3 multiplied by 2 square. 2 2s are 4 minus 2 plus 4 into 3 is 12. 4 minus 2 is 2, 2 plus 12 is 14. So 14 radians per second is the angular velocity. Next, angular acceleration at t is equal to 2. Put time as 2 over here. 6 multiplied by 2 plus 2, which is nothing but 12 plus 2. Coincidentally, this also came out as 14 radians per second square. This is just coincidence. That's all. Till this point, everything clear? Till this point, everything clear? Okay. Last part, average angular velocity. How do I find that? For that, I need angular displacement. Without that, I cannot do it. So what is initial angular position? Put time as 0 in this. So it will be 0 square minus 2 multiplied by 0 plus 0 cube. It is 0 radian. The angular position at 2 seconds, put time as 2. So 2 square minus 2 multiplied by 2 plus 2 cube. 2 square 4 minus 4 0. 2 cube is 8. So it is 8 radian. But the question is about average angular velocity, which is displacement upon the time interval. Displacement is 8 minus 0. Time interval is 2 seconds. Hence the answer will be 4 radians per second. Average was 4. Instantaneous at that time was 14. Angular acceleration was 14. That's how you do it. Okay. These are some of the questions usually which you get on these variables, omega, theta, alpha, etc. Now, in a very peculiar case of circular motion, which is uniform in nature, uniform circular motion. If you ask me, is the velocity constant? I will say the answer is no. Why? If you ask me, is the velocity constant? I will say no. Velocity is changing in direction. That's the reason. But the magnitude remains constant. The magnitude is constant. Basically, the speed is constant in case of uniform circular motion. Hence, if you ask me, is there any centripetal or tangential acceleration? I will say tangential acceleration certainly is 0. Also, the tangential force is 0. But the centripetal acceleration, which is v square by r, is 100% not 0. Is this constant? The answer is no. Centripetal acceleration, only the magnitude is constant, but if you talk about the vector, is changing in direction, is going to change in direction. Centripetal is always directed towards the center. Once it is here, then it is here. So even the centripetal acceleration's direction keeps changing. A lot of people think centripetal acceleration is constant. Yes, only in magnitude, not otherwise. Also, since tangential is 0 and centripetal is there, hence I can say clearly from all of this that the net acceleration is the centripetal acceleration. Net acceleration is the centripetal acceleration, and the net acceleration will be always perpendicular to the velocity at every given instant. Every instant, the net acceleration will be perpendicular to the velocity. All of this only works for uniform circular motion. Do not forget this part. It's only for uniform circular motion. What about omega? What about omega? What about omega? Well, omega is going to be a constant because it covers equal angles in equal time. So in one rotation, if you do this for one rotation, angle covered will be 2 pi radians. The time will then become the time period. So therefore, you get this very interesting equation called as omega is 2 pi by t. Omega is 2 pi by t, where this t is also called as the time period. This is also called as the time period. This is called as the time period. You have one more interesting term here, which is called as frequency, and 1 by time period is f. This f stands for the frequency. How many times per unit? How many times does it go per unit time? 5 times in 1 second is 5 hertz of frequency. 10 times in 1 second it completes circles. It is having 10 hertz as the frequency. So that is your frequency, guys. That is 1 by t. Again, an important formula. Lastly, if you ask me alpha, alpha is 0, of course. There is no change in the speed. So alpha is 0, obviously. Angular acceleration. Angular acceleration is 0, obviously. All these are important formulas again. Let's look at some questions based on this concept as well. If a fan rotates at 20 hertz, find and the blades have length of 50 centimeter. Find number 1 omega, number 2 time period, how much time it takes to complete one rotation, number 3 tangential speed of the tip of the blade, and velocity at the center of the fan, This is what you have to find. Yep, I think pretty much it. That's it. Let's see if you can figure it out. Question on uniform circular motion. Let's start with this. Fan rotates at 20 hertz. 20 hertz is frequency. So frequency is basically 20 hertz, and frequency is also 1 by t. I just told you right over here, the formula for frequency is 1 by the time period. So that's it. Use that. Time period will be 1 by 20th of a second. So that's it. That is the first answer, time period. What about omega? Omega is nothing but 2 pi divided by t. So it will be 2 pi divided by time period, which is 1 by 20. 22s are 40. So 40 pi radians per second. That is your omega. Well, that is the first answer. What about this? See, if this is our fan, Okay, this is our fan like this. This is the center. This point will have very large speed. This will not have so much. This will have even less. This will have zero speed. So technically speaking, the velocity at the center will be zero, but the velocity, this is the tip. The velocity at the tip using omega r formula, omega is 40 pi, radius is 50 centimeter, which is 0.5. 0 is swallowed by this decimal, 4 5s are 20. So 20 pi meters per second. So that's the velocity of the tip of the blade. That's the velocity of the tip of the blade. Is that clear, everyone? Okay. Somebody is asking, is omega a vector or a scalar quantity? Okay, I'll tell you what it is. Just 1 second. Okay, just imagine okay, I just have a book over here and I will define omega as a vector quantity for now. Let's find out whether it follows the rules of vector addition. How? If something rotates like this, something rotates, let's say like this, imagine this in 3D. Curl your fingers of your right hand in that direction. Curl your fingers of your right hand in that direction. Your thumb will point somewhere. Your thumb will point somewhere. That is the direction of omega. Your fingers point in the sense of rotation. Sense of rotation. The thumb points in the direction of omega. Now, if this is how omega, alpha, etc. are defined, let's do certain operations on the book over here. Okay, on this particular book, or yeah, I hope you are able to see this. Right now the book is facing flat, horizontal, and if I slightly tilt it towards you, you will be able to see the text upright. You can read it properly. I'm holding it like this. I will give an omega of 90 degrees in the upward direction. Omega is up, that means my thumb is up. That means my fingers curl like this. Fingers curl like this. So I have to turn it by 90 degrees in this direction. The sense of rotation is this way. Okay. So the book which was like this, turned like this because omega is pi by 2 radians in the j cap direction. In the j cap direction. Now I give an omega of pi by 2 in the k cap direction. K cap is towards you, thumb is towards you. So if I curl the fingers, it goes like this. So what are the operations? J cap pi by 2, pi by 2 j cap, pi by 2 k cap, pi by 2 k cap. So the book went like this. I hope you are able to see that. The book went like this. This book is now upside down. And this cover of the book is facing this side. Now let's repeat the same thing, but in a different order. I'll first do k cap and then do j cap. K cap is towards you, k cap pi by 2 radian. So I have to turn the book, which was like this. Okay, it was like this. So k cap is towards you, thumb is towards you, the fingers curl like this. So I'll turn the book like this. Then I will perform the j cap operation. J cap is there, pi by 2 radians is like this. Wow, look at it. Now the book cover is facing you. This is crazy. If I first rotate like this, then I rotate like this, the book orients like this. But if I first rotate like this and then rotate like this, the book orients like this. So j cap plus k cap is not the same as k cap plus j cap. That means the vector addition is not commutative in nature. Hence it does not follow the rules of vector addition. Hence it is not a vector quantity. Hence it is not a vector quantity. Guys, got it? This is crazy. But the interesting part is, If I rotate it by a small angle, 1 2 degrees, imagine in the j cap direction 1 degree, then in the k cap direction 1 or 2 degrees, okay, in the k cap direction, first I rotated it like this, then I rotated it like this. Or I first rotated k cap 2 degrees and then I rotated 1 degree in j cap. You will see it's roughly the same. Whether I rotated it first like this and then like that, or first like that and then like this, it's almost the same. Hence, it is a vector for small angles, not for large angles. So keep this in mind. Keep this in mind. Omega average is not a vector because it does not follow the rules, but omega instantaneous is a vector. Is a vector. Keep this in mind. It is a vector. Here it is not a vector. Got it? Clear? Okay. SHM and waves, everything. Helix, October is the month. Sound waves, light waves, or wave optics. Ray optics is done already. SHM, all that in October. And even gravitation will do. Yeah, it is a small thing. Great. Actually, everything is a tensor, Nikhil, that way. Let's not get there because then you will be like, sir, what is a tensor and everything? Okay. Where is it? Okay. All this is done. This is also done. This is also done. Now let's go to the last concept. Yeah, we'll have a break and that break will be the end of the class. Okay. It will hardly take us 10-15 minutes more. Do you want a break and then continue for 10-15 minutes, or should we continue for 15 minutes and finish off the topic? I think that will be better. What do you say? Once and for all. Yeah, gather up some energy, guys. Quickly smash the like button if you are new and not yet subscribed. Subscribe to the channel. Honeymoon, your passion for teaching has helped me a lot in JEE physics. Physics has been my nightmare ever since I watched your sessions. It all makes sense. Thank you so much, Capto. I'm so glad, Honeymoon. I don't know what your name is actually, but means a lot. And I'm so glad I brought in the change through YouTube. Okay, on your way to IIT, obviously, Anshuman. Every day is one step closer, one step closer. Yep. Every lecture that you watch over here is bringing you one step closer to IIT. And trust me, it is actually like that. Every day you don't do anything, you don't watch the class, you miss it, have a backlog. In fact, taking a backlog is taking a step back from IIT. You don't do anything, you're just not moving. You are making more mistakes, you are not improving, you are taking a step back. So every day you have to proceed two steps ahead. And that day will come, guys. Next year, or maybe 2 years, if you are 11th. Where you will be inside the IT campus, you will be making a story, a reel, and you will be posting it proudly on your status or on your social media account. Finally, the day comes where I actually step inside IT. And there will be goosebumps. There will be goosebumps on you. I mean, really. Everybody will feel proud. Your parents will be proud. And that story or that social media post is something which will be worth it because you have put in that effort. It's not about just walking inside an IIT, it's walking inside the IIT with your ID card inside. Yep. Right? Let's go ahead. Let's talk about something called as the centrifugal force. If you remember, there was something called as a non-inertial frame. There was something called as non-inertial frames. Non-inertial frame in which Newton's laws of motion are basically invalid over there. And because Newton's laws of motion are invalid, you correct it, you validate by a fictitious, not a real force, which is also called as pseudo force, and that's how you are able to apply Newton's laws. So you just say then, okay, fine, sir, I got it. Net force plus our pseudo force which is there, sir, that will give me our mass times acceleration. That is what you say. This is what our traditional approach was. Now what happens is, even when you are rotating, a rotating frame, not even accelerated, just a purely rotating frame is a non-inertial frame. Yes, any rotating frame, a rotating frame is a non-inertial frame. So imagine there is a pandu sitting inside a frame, and that frame is rotating. This pandu is a non-inertial pandu. So Newton's laws for him are invalid. So in order for him to make Newton's laws of motion valid, so for this non-inertial observer, if he is drawing the free body diagram of some object, there will be many forces, maybe like this, etc. Apart from this, there will be some acceleration maybe. This might be accelerating maybe here like this. So this is some acceleration with respect to this observer. You will apply one more pseudo force, and basically you will apply the pseudo force, and that pseudo force is called as the centrifugal force. It is always opposite to the direction towards the center. Towards the center is centripetal. Petal is towards, fugal is away. So you will go away from the center. So if this is the axis of rotation, you will go away from the axis like this. So this is the direction of that pseudo force. And this pseudo force value is m omega square into r. What is m? M is basically the mass which is being looked into. So this is that mass which you are looking at, that is that m. Omega is the angular speed of the frame's rotation. R is the distance from which that mass is kept from the axis. So m omega square r is the value of the centrifugal force. As simple as that. Okay, something which you should keep in mind. Is that clear, my dear warriors? What is this centrifugal force? It's nothing but a pseudo force, and the pseudo force always acts away from the center, and the value is m omega square r. Very, very easy peasy. Okay, now let's do a question based on this. Very, very interesting question. Imagine a nice giant wheel . Imagine a giant wheel and there is a cabin, and that giant wheel is rotating like this slowly. Okay, it is rotating like this, and the rotational speed is omega. The distance from the center till here, maybe it is r. Okay, the radius is also given, and you are inside that cabin, and we'll try to think what kind of forces will that person experience, because he is in a rotating frame. So if you are in a rotating frame, you will experience pseudo force. So let's try to figure out what kind of pseudo forces, what kind of other forces, etc. are there. Imagine there is a person over here. Imagine there is a person over here whose mass is basically m. Okay, mass is basically m. What are the different forces acting on him? Obviously, there will be a normal force, there will be mg force, there will be mg force, there will be normal force like this. Apart from that, pseudo force is there. Because you are rotating it, centrifugal force in that rotating frame will push you outwards. That lift frame, that cabin frame of that giant wheel is a rotating frame which is non-inertial. So centrifugal force will push you outwards. So guys, here outwards means like this. So centrifugal force is here. Here the centrifugal force is like this. At the top position versus the bottom position. So first let's talk about the top position. How will the equation look like? Normal plus the pseudo force will balance mg. Therefore, normal will be mg minus the pseudo force. Whereas, if you go at the bottom, what you will notice? Normal is balancing mg plus the pseudo force. Here it is mg minus, here it is mg plus. That means this normal is more, this normal is less. So a person who is in that cabin, in that giant wheel, when he reaches the top, he will feel lighter because the normal force is less. He will feel like he's slightly become lighter. But the person who has reached at the bottom of the giant wheel, the normal force will be more than weight of that person. So he will feel a bit heavier. As he's going down, he will feel pressurized a little bit. Yes. So that is what is interesting in this because of the pseudo force. In fact, you can calculate it. How much will it be? It will be mg minus m omega square r. Here it will be mg plus m omega square r. There is also one interesting aspect to this. There is a unique omega for which normal will be 0. You will feel complete weightless. You will feel complete weightless if this normal force becomes 0. Imagine if it becomes 0, that means mg minus m omega square r will become 0. Mm cancels, g will become omega square r, or rather omega will become root g by r. If you rotate the giant wheel with this speed, normal force at the top will vanish. The person on the top will feel he's floating at this particular speed. Not at the bottom. At the bottom, the normal will be more, but at the top, for a moment, he will feel that he is weightless. For a moment, he will feel that he is weightless. Isn't this interesting, guys? Everyone? Is it absolutely clear how this pseudo force, centrifugal force works? Let's do one more question based on that, and again on amusement park. So this is another very unique application of centrifugal force. I have seen this kind of adventure in amusement parks where there is a vertical cylindrical drum and it can spin, and you are on the inner walls of the cylinder. You are on the inner walls of the cylinder. So just imagine this is one of the walls of that cylinder. You are looking at it from the inside part. Imagine that there is a person here. Imagine that there is a person leaning against that wall. He's just resting against that wall. Now that cylinder begins to rotate, the person also moves along with that vertical wall. The person will also go like this. Are you able to visualize it? He's just leaning over there. He'll also begin to rotate. Now, as that person begins to rotate, what is happening? He will experience a centrifugal force in the outward direction. So you will see that there is a very nice centrifugal force. Centrifugal force in the outward direction. So he will be pressed against the wall. He will get pressed against the wall, against the vertical curved wall, vertical curved wall. Because of which what will happen is that person will experience a normal force like this. Will experience a normal force like this. Are you able to understand? He will experience a normal force like this. Now, apart from the normal force, obviously the person has its own weight, mg. That weight will try to bring the person down. But if there is a ground surface below, solid surface below, there will be another normal force from here. But just imagine, if you do not provide a surface from below, the normal force won't be there. This person will slip. What will happen? The person will fall down. Now, if the person tries to fall down, who will act? Friction. Friction will avoid that slipping. So you will see the frictional force will act like this. The frictional force will act like this. Vertically up. If you are able to balance mg, the person will be hanging in air even though there is nothing below. Even though there is nothing below, the person will be hanging. Just imagine this guy right over here, guys. Imagine this guy right over here. He's just going round and round, and he has not kept his feet on anything. He's just lying there. Isn't it amazing? For a person standing outside, centrifugal force will not exist, because for a person standing outside, ground frame is inertial. He will talk in terms of centripetal acceleration, not centrifugal. Not centrifugal. Because outside frame is a ground frame. For the person, he experiences centrifugal force. He is on a non-inertial frame because he is rotating. And everything balances perfectly. So in this situation, I can just say the normal force is that pseudo force, which is m omega square r. Also, mg must be at least equal to the friction. In the limiting case, it is Fs max. So it is just on the verge of slipping. So Fs max is mu into n. Normal force is m omega square r. This is basically mg. M and m cancels. So from this, I will get the value of omega as what is it? G by mu into r. So this is the minimum omega with which you should rotate so the person does not fall down. He stays there intact. He does not slip. So this person over here doesn't fall or slip with enough rotation. This is another amazing adventure ride. Is that clear, everyone? How this problem works? This is completely based on centrifugal force. Great. So we have done most of the questions. Centrifugal force, banking, unbanked roads, right? We have done vertical motion, pendulum motion problems. We have done other numeric problems of non-uniform circular motion, finding the radius of curvature, tangential, centripetal, forces and acceleration and their formulas. Okay, all these things are the main concepts of circular motion. I hope you guys enjoyed this lecture, right? I hope you guys enjoyed this lecture, and make sure you are smashing the like button, subscribing to the channel, and more importantly, download the PDFs from the Jungle Book. The Jungle Book is a sheet of all the lectures, all the PDFs, all the notes, any sessions, you will find it here, and this will be updated in the days to come. Also, the scholarship test which is going to happen, which is the biggest, lakhs of students participate. So you get your ranking, goodies, prizes and scholarship to be won. Okay, and counseling and many free things are there only when you attempt this. Don't think, sir, I will get a bad rank. There are a lot of goodies at least for participation purposes. But only if you write the test. If you just register and don't write, then you will not get the goodies. At least get 0 marks. At least you will get some goodies. Okay, cool. Offline on 29th September onwards at different centers across India. Preferably give it offline. If you can't, if you are far away or there is no center around you, then give it online. It's one and the same thing. I've told you the pattern, the exact nature of the test in a separate video. Please watch that dedicated video. Cool? Right. Chalo. So we had an amazing time. When will I take modern physics? Maybe towards the end, maybe November. What force will the person standing outside look at the centrifugal force? He will not look at it as centrifugal force only. He will just say, where is it? He will just say, this normal is equal to mass into acceleration. Acceleration will be omega square r. He will not see this. He will see centripetal acceleration. He will say force is equal to ma. A will be omega square r. A will be omega square r. Equations will be same. Just the way he looks at those equations will be different. That's all. Cool? Okay. I hope you learnt a lot. A lot of concepts are cleared and misconceptions are specially thrown out of your head. Okay. So see you guys for the PYQ session, and magnetism starts next, and after that we'll go to center of mass, rigid body, SHM, all of that. Cool. Bye bye. Take care. Have a great time. Yeah. Hasta la vista.